Hello students, welcome to Engineers Arena. This is design of RCC, lecture number 2, properties of concrete. In last class we studied about the properties of one of the properties of concrete, and that is EC, value of EC, short term elastic modulus of concrete. And in this lecture we will study about different modulus of elasticity of concrete. Okay, we'll study different modulus of elasticity of concrete. For this, I will be drawing one graph of stress and strain. I'm drawing one graph for stress and strain for concrete. Okay, so this is stress and this is strain. Okay, so I'm taking this for first point. This is let this be as theta1. Okay, I'm taking any of this point, any of this point, and joining this to origin. Okay, let this be O. And what is this? This is theta2. This is theta1. And thereafter, I'm taking any one point, and we are just drawing a tangent. And this is equal to what? This is equal to theta3. Okay. Then what is theta1? What is theta1? Theta1 is the initial tangent modulus. Initial tangent modulus of concrete. Okay. Initial tangent modulus of concrete. Okay. Theta2 is nothing but ES. It is the second modulus. Second modulus of concrete. Modulus of elasticity of concrete. I'm writing as modulus of concrete. Okay. And now theta3. What is theta3? Theta3 is the tangent modulus of. These are the names. Tangent modulus of concrete. Now a question comes: why we are defining these elastic modulus of concrete in three different types? Okay, why we are defining it? Actually, what happens in the field when the loading conditions are different. That is, for if we want to load a machine on a roof of a building, then its foundation should be the load which comes on the roof is dynamic, basically dynamic loading, because the machines are huge and heavy. So the load which comes on the concrete is heavy. Okay, so we required a dynamic modulus of elasticity. This theta1. You can see theta1 is greater than theta2, and theta2 and theta3 might be equal. They are not interrelated actually. But theta1 is greater than theta2 and theta3. Okay, but theta1 is for what? This is for dynamic modulus, dynamic loading. You can say dynamic loading. Okay, loading, dynamic loading. It is used in where? It is used in resonant frequency test. Resonant frequency test. Kindly bear with my handwriting. Resonant frequency test. And theta2 is what? Theta2 is second modulus of concrete. Theta2 is second modulus of concrete. This is nothing but ES. Sometimes it is known as EC, is equal to, which you have already studied, 5000 under root of 6. This is nothing but second modulus of elasticity of concrete. And this is what? This is theta3, tangent modulus of elasticity of concrete. What is happening? You can see that is wherever I draw a tangent, that will be equal to theta3. This is theta3. This is theta3. Both of them theta3. So this is used for incremental loading. Test. What we do? We load a pile with load P, then P plus X, then P plus 2X. Likewise we do it. Okay. So we are increasing the load. So this value of theta3, we can call it as E3. If you are calling this as E1, we can call this as ES or E2, and we can call this as E3. E3 is what when there is incremental loading. That is tangent modulus of concrete is used when there is incremental loading. So for different types of loading, we have defined different types of elastic modulus of concrete. Okay. Now very quickly we'll moving towards the permissible stresses in concrete. What are the permissible stresses in concrete? Permissible stresses in concrete. So I've already told you to keep with you at IS 456-2000, IS 456-2000. You can refer to page number 81, table number 21. Okay, you can refer to page number 81, table 21. And change the color. Okay. So you can take out that page IS 456-2000, IS 456-2000. So there is a table number 21 for M15. I'm writing for 3 grade of concrete only, and this is what? This is sigma CBC, and this is what? Sigma D, and this is nothing but the grade of concrete. Okay, so you can see in the table that for M15 it is 5 and sigma D is 4. For M20 it is 7 and sigma D is 5. For M25 it is 8.5. This is 6. Okay, now my question is, you can see that what is sigma CBC? Sigma CBC is first, sigma C is critical bending stress in compression. Critical bending stress, critical bending stress in compression. Okay, and what is sigma D? Sigma D is the direct stress. Sigma D is the direct stress. We will use this in column using sigma CBC. Okay, now my question is that you can see that this grade of concrete is M50, sigma CBC is, we are taking only 5. That is factor of safety. We are considering factor of safety is 15 by 5, that is equal to 3. Similarly here 20 by 7, 25 by 25, that is approximately 3. And in this case where in sigma D, what is the factor of safety? This is factor of safety 1, this is factor of safety 2. What is this? 15 upon 4, approximately equal to 4, but greater than 3, right? It is greater than 3, and thereafter 20 upon 5 equal to 4. This is also greater than 3. Why is this? Why so? Why there is difference? Why there is difference in factor of safety? So it is a very simple reason. See, in sigma CBC, what is happening? The concrete is it is bending, beam is bending. Okay, then what will happen? Stress diagram will be like this: sigma CBC, this will be sigma CBC. And in direct stress what will happen? This is all equal to sigma D, compressive sigma D, right? Now you see that in this case there is only one extreme fiber which is having maximum stress, whereas in this case we are having all the stresses, in all the fibers there is maximum stress. Therefore factor of safety in this case should be greater, and therefore it is factor of safety. You can see that this is greater. This type of question might be asked to you in interviews. Okay, so you must know this. Okay, thereafter one of the more properties of concrete, that is tensile strength of concrete. Tensile strength of concrete. What is tensile strength of concrete? That is equal to FCR is equal to 0.7 under root FCK. You know what is FCK, already told, Newton per mm square. This is actually the tensile value which the concrete actually in actually when we will design, we assume that tensile strength of concrete is 0, but actually there is some tensile strength in concrete that is equal to 0.7 under root FCK. Now let me explain you this in detail. You must have studied flexure formula in strength of materials. The basic formula you must be knowing it. Flexure formula. What is this? M by I is equal to sigma by Y is equal to E by R. Suppose we are taking a concrete section. There is no steel in it. Concrete section, only concrete. Okay. Then this value, and we are loading it. Suppose, and then the beam bends. So this bending stress is basically FCR. Okay. This is sigma in tensile zone. This is FCR. Okay. This is also known as since this is CR, this is also known as cracking bending stress.